Hi everyone, welcome to my channel. So today we are going to continue the optimizer series. So we have learned about gradient descent, stochastic gradient descent, and mean width gradient descent. So going further, all optimizers will have that minimized gradient descent. So what I'm trying to say, to calculate the loss, actually we need to uh, get the batch size for time interval. Some um, for time interval as the number of base size of the data we have mentioned, that particular data actually uh, we we need to calculate the loss and do the backward propagation. So yes, so it is quite advanced than mini batch gradient descent. So it is gradient descent with momentum. So here actually what happens, so in mini batch, this is if we are going to consider this is the global minima. So what happens, uh, while doing the convergence, uh, as we are applying batch size, mini batch size gradient descent. So there will be little noise while come to the global minima. If if we are gonna plot weight with respect to loss graph, so it will come to the global minima, but there would be noise somewhat. So what we are trying to do here is, by applying stochastic gradient descent with momentum, we are trying to reduce this we are trying to reduce this noise. So actually we have much more noise inside, right, as you can see. So we're just trying to use the momentum technique in order to avoid that noise and try to smoothen the curve in order to reach the global minima. So it will help us to converge more properly with less time, and the process will be very much smoother than the mini batch gradient descent. So here what we are doing, actually, uh, so here what we are doing, uh, this is the basic weight optimization that we already know. This is that I have taken t at time interval, uh, because we need to apply exponential weighted average in order to smoothen this curve, right? So this is the basic weight optimization technique, that this is the time interval this is the time interval of weight. So this is the weight of the previous time stamp, and we need to calculate the derivative loss. This is the basic traditional weight optimization that we already know. Let's see how it is going to behave after applying exponential weighted average. So actually, as you have already know, I guess, in machine learning concept, there is a concept in time series, that ARIMA model. So actually what it is, like what it was doing, it was trying to give some impact or give some importance to the previous data, right? So here also we're doing the same thing by adding exponential weighted average. So this is basically base size data. So for, like, you can consider 1,000 data we have mentioned in base size. So first 1,000 data, then second 1,000 data, then third 1,000 data. So third means I'm saying the first time interval, the this a1 will be data to be considered to calculate the loss and do the backward propagation. Then for second time interval, it will do the will get the second 1,000 data at the second time interval and calculate the loss and do the backward propagation. So that will do. This is the basically a is a here a is all the data set, and here is the time interval in which we are getting those particular data, right? So what we are doing, we are applying somewhat the momentum. If you know the physics concept of momentum, so we're just applying the same thing. So we're just considering, okay, somewhat v as velocity, you can say. So v is here, you can say, as constant. So we are time interval 1, the first time interval we are getting a1 data, right? So for second time interval, we are applying one hyperparameter tune, that is beta. Beta is nothing, you can hyperparameter tune, basically we take 0.95. So how it is gonna uh, give the more importance to the previous data, let's see. Okay, so this is VT1. So first time interval we are getting this data A1 data. For second time interval we are just giving some impedance, like adding, like multiplying beta to the previous data bit VT1, and somewhat less uh, importance to our recent data, this is V2. So beta is beta A1 and one is beta A2, right? For calculating next time stamp for T3, so you can say beta multiplied by VT2 means the second, the previous. If this is the uh, third timestamp data we're calculating, so the previous data will be second time stamp, right? So for second time stamp, we are considering beta VT2 1 minus beta the recent third, the like third interval timestamp data, right? So for this VT2 we have already calculated this, we are just applying this thing in place of VT2, and we are put, as we know the beta is the hyperparameter tune. So suppose we are giving more importance to A1, so we can take hyperparameter tune as 0.95, and if we are going to substitute 1 minus beta, it will give you 0.5. So as you can see, by multiplying 0.95 we are giving more importance to the previous data and less importance to the recent data. So by using this type of concept, actually we are giving we are actually taking care of uh, previous data set as well, so it will do the smoothing concept as well. uh, okay, so this is the basic way of applying exponential weighted average. So let's see what internally happens when you call stochastic gradient with momentum optimizers. So this is the traditional uh, like actually this is the traditional weight optimization that we had already. So here actually for previous weight what we have already considered, so how to update minus eta VDW. So VDW is nothing but here is the exponential weighted average. So what is VDW value here? So VDW value is nothing but same, we are applying previous timestamp, so previous data we are applying beta, let's not applying, is multiplying beta to the previous timestamp 1 minus beta to that loss that we have already that we usually do the loss calculation, right? So derivative loss with respect to the weight of previous data set. So this is, so we are giving less importance to the derivative part, and we are giving more importance to the this particular variable, right? So initially actually this is the this is the basic formula used in stochastic gradients momentum. So initially actually when we are calculating like the before the first iteration, you can say the first iteration in the epoch, it it will be considered as VDW as 0. So for iteration t in first epoch or any epoch, you can say, so compute DW on the current mini batch. For the current mini batch, so how to calculate? So this is the basic traditional the basic um, updation formula for VDW. As you can see, where beta VDW VDW is initially considered as 1, like sorry, initially considered as 0. As you can see, I have already mentioned it. So we're applying beta VDW t minus 1, 1 minus beta, and the um, derivative function. So it looks quite complicated, but if you see and think in logical way by applying how it is performing exponential weighted average, so it is kind of easy, so you can do that. So how you are achieving smoothing by this? So this is the weight optimization, that previous weight n is nothing but the eta, the learning rate, into VDW. VDW is nothing but this one, the exponential weighted average that we are calculating by this formula. The same thing can be applied as bias. As we already know, the bias is also something that we need to update while doing backward propagation. So yes, for B also, for bias also we can apply the same formula. So by doing this we are achieving smoothness. uh, to reach the global minima here. Okay, so this is all about stochastic gradient descent. So if you have any doubt, you can comment me. I will try to solve your queries. Thank you guys.